Okay, lesson 1-4, continuity. For the warm-up, evaluate each limit. So whenever we see a limit, always start with direct substitution. Plugging in 4, 2 times 16 minus 20 minus 12 all over 0, looking like it would be an indeterminate form. 32 minus 12 is 20. 20 minus 20 would give us 0 over 0. So indeterminate form, do something algebraically. Which is 4. If 4 minus x is a factor on the bottom, it's more than likely going to be a factor on the top. So we'll start with x minus 4. And then negative 4 times positive 3 would give us negative 12. 2x squared. 3 minus 8 gives us negative 5. Now you saw this in the warm-up worksheet, or the prerequisite worksheet I gave you. X minus 4 and 4 minus x are opposites of each other. So limit as x approaches 4 of negative 1 times 2x plus 3. Now that we've eliminated the 0 over 0, we can do a direct substitution. So the opposite of 2 times 4 is 8 plus 3. So our answer here would be negative 11. So just a reminder, indeterminate form doesn't mean a limit doesn't exist. It just means we might have to do something more to determine if it does or does not exist. We're going to talk about these two functions in today's lesson, so I'm actually going to leave them be for right now. Okay, one-sided limits. One-sided limits are used to describe the behavior of a function. When we're discussing one-sided limits only, positive and negative infinity are acceptable answers, and you'll see why. The notation for a one-sided limit, you did see this last year. Limit as x approaches c. That little minus sign means from the left-hand side of the function. Limit as x approaches c, the plus sign means as we look from the right-hand side of the function. And we've already studied this, just haven't given it a formal definition. The limit exists if and only if the limit from the left-hand side and the limit from the right-hand side are the same value. Okay. So let's look at some piecewise functions. We'll look at the graph. Always start at where the domain switches. So when x is equal to 0, this would give me negative 1 on the quadratic. When x is equal to 0, it would give me y value of 0 on the line. So 0, negative 1. That also happens to be the vertex of the quadratic. So I have a parabola to the left of 0. And then I would put an open circle at the origin. And I just have a line with a slope of positive 1. So as x approaches 0 on the left-hand side of the function, what is my y value approaching? Negative 1. So that would be the limit from the left. As I focus in on 0 and approach it from the right-hand side of the function that's graphed, my y values are approaching 0. Since the left and the right-hand limit do not agree, we would say the limit as x approaches 0 does not exist. And we've looked at these graphically already. Again, that's why I said you know, we just never gave a formal definition to it. Okay, given a rational function, evaluate each. The limit as x approaches 5. Every single time we see a limit as x approaches c, start with the direct substitution. Give us 0 on the bottom. This is not indeterminate form. Okay, number over 0 automatically means that the limit does not exist. In addition to that, however, this very specific over 0 forces our one-sided limits to be positive or negative infinity. So what we're going to do, I'm going to factor the denominator. We know that's difference at perfect squares. I cancel out the x plus 5's. And my function now simplifies to 1 over x minus 5. To determine the limit from the right-hand side. Okay, I already know that the one-sided limits are going to be positive or negative infinity. If I take a number bigger than 5, so let's say 5.1, if I plug it into my simplified function, I'm going to get a positive value on the top and a positive value on the bottom as well. So be positive infinity. As x approaches 5 from the left-hand side, so let's pick a number really close to 5, 4.9. Positive 1 on the top, 4.9 minus 5 would give me a negative value in the denominator. So my limit is going to be negative infinity from the left-hand side. Okay, limit as x approaches negative 5. We'll use our simplified function. A direct substitution would give me 1 over negative 10, so that is the limit. If the limit exists, then by definition, that's the limit from the left and the right as well. So when you're asked to determine one-sided limits, we can still always start with a direct substitution. If the direct substitution gives us a number, it forces that same value to be the left and the right side limits. If that limit does not exist, then the one-sided limits could potentially be different values. Now when we look at the graph of this function, we've simplified the function into 1 over x minus 5. So this is what we've talked about, functions agreeing everywhere except one point. The limits give us a lot of information about the behavior of the function. I would have 1 over x minus 5, 1 over x, my parent function is the inverse. It's a horizontal shift of 5 units to the right. So my vertical asymptote has shifted to the right. And the importance of this, okay, if you looked back at the original and plugged in negative 5 over 5, you would get 0 over 0. That means the function doesn't exist at negative 5. So at negative 5 and negative 1/10, I'm going to have a hole on the graph of the function. So I use my parent function, but I just need to take into account what these two limit statements tell me. And we'll talk more about this. I have a note to wrap these two things up. Okay, so the limit as x approaches 0. This was the warm-up problem. Direct substitution gives us 0 over 0, so indeterminate form. Let's look at what the graph is. Let me start here actually. If I look at the absolute value of x, think about what the absolute value function does. It makes positive any number that starts out negative. So any number that's less than 0, the absolute value takes the opposite of that negative number. If we start out with a number that's already positive, the absolute value function doesn't work at all. Okay? So this is what the absolute value function is defined as. So at 0 is where my piecewise function, the domain of my piecewise function, is changing. So let's look at what's happening. At 0, this function, absolute value of x over x, does not exist. For any number bigger than 0, however, I'm taking x and dividing it by itself. So I would have a hole at 0, 1, and then my y value, if x is positive, is just positive 1. If I look at any number less than 0, the absolute value function would be negative x, the opposite of the value. Negative x divided by x would give me a y value of negative 1. I have a hole at 0, negative 1, because the function doesn't exist there. So let's look at the one-sided limits. As x approaches 0 from the left-hand side of the function, the y value is negative 1. As x approaches 0 from the right-hand side, looking at the graph, all the y values approach positive 1. So direct substitution gives us an indeterminate form. Looking at the graph of the function, we determine that the limit doesn't exist. Okay, continuity. Continuity is a big one. Think about what to be continuous means. If you think of continuous functions, and you studied functions a lot last year, continuous would be, if I trace the graph of the function, we would never have to lift our pencil. No breaks, no jumps, nothing that's messing up, for lack of a better term, one continuous graph. If I asked you, if we look at the graph from example 2, we had a whole and an asymptote. We're always traced left to right. If I were to trace this graph, I would have to lift my pencil as a whole, finish it, and I would have to lift my pencil to take into account the asymptote as well. So these would be discontinuous. This would be an example of a discontinuous function. This would be an example of a continuous function. A function is continuous at a given point if and only if 3 conditions have to be satisfied. F of c exists, the limit as f of x exists, or the limit as x approaches c of the function exists, and the y value of the function and the limit of the function are the same thing. So let's look at 3 examples of these cases. Identify why the following functions are not continuous at x is equal to, that should not be 0, but rather c. Okay, so 3 conditions for continuity. The function exists at the point in question. The limit as x approaches c of the function exists, and the y value and the limit are the same. Okay, so let's look at this. Here's c. Here's the value of the function, so f of c exists. The limit as x approaches c. Okay, from the left-hand side of c and from the right-hand side of c, we're approaching the same value. So the limit exists. But if I gave these numbers, let's just say 2 and 3, the value of the function is at y is equal to 2, but the limit of the function is at y is equal to 5. And the value of the function are the same. Okay, when we look at this one, at the 3 conditions, f of c, well, there's no corresponding y value when x is equal to c. So it fails the fact that the function exists. When I look here, we'll give that a value of 4, give that a value of 2. F of c exists. Okay, when x is equal to c, its corresponding y value is 4. When I look at the limit as x approaches 0, let's look at the one-sided limit. From the left-hand function, so from the left-hand side of c, the y values are approaching 4. Side of c, the y values are approaching positive 2. So it fails the fact that the limit of the function has to exist. Okay, we'll stop there for now.